Good morning, everyone. Welcome back. Before we start, a number of people, I will say, were asking questions. In fact, it was great. Yesterday, I think there were coffee breaks, but I didn't see any of them because people were talking to me in between, so that was fantastic. People were asking for the slides from the lectures, and so let's see. They've been posted here. So if you go to the school page and go to lectures, then, for example, if you click on lecture notes, the version that I sent yesterday is up there, and then I'll update them after today and tomorrow, and then after tomorrow there'll be the final set. Also, I'll post later on maybe like a set of 10 or 12 exercises or something in case you're looking for some homework or something. So, all right, so those will be posted there. Let's see. There we go. Okay. All right, so let's try to remember where we were yesterday. In the first lecture, we discussed the Einstein equation, derived the constraint equations, okay? And again, right. So the constraint equations live on a Riemannian manifold. You have a metric G and a second fundamental form, or a symmetric 0,2 tensor K. So that's where the constraint equations live. And we discussed then how to interpret these quantities in terms of the initial value problem, initial data, for starting from a manifold with this data and constructing space-time satisfying the Einstein equations. Okay, so we discussed that yesterday. So the focus was then on studying the initial data. And the point was, those constraints, again, I said this yesterday, but just to emphasize, the constraint equations that we derived give you equations that have to be satisfied between G and K to be allowable initial data to evolve to a space-time satisfying the Einstein equation. So the point is that the data is not free, okay? This data is not fully free. And one of the goals might be in sort of studying the constraints is to identify, so what parts of the data then are free in some sense to specify, all right? So after we did that, we started to discuss then solving the constraints. We discussed using conformal transformations to produce some solutions. And then at the very end, we started talking about the conformal method. And that's where we'll start today. So the goal today is to discuss a bit about the conformal method, to use it to do a conformal gluing construction. And then the last topic will be non-conformal methods. And we'll just see how far we get. So I'm not going to rush through to slide 89 today, so please ask questions, as Piotr said. All right, so just in 3 dimensions, so it's spatial dimension 3, for example. You can do this in any dimension. The constraints form a system of 4 equations for 12 unknowns. And as we said yesterday, we may try to put in some of the data as free and then write the system out as a determined system instead of an undetermined system. And so the question is, what parts of the data would be maybe free, and then what parts would you solve for? Okay? So I mentioned this yesterday, but let's review. Part of the data will be, as we'll see, in terms of the metric G, part of the data will be specify the conformal class of G. So specify the conformal class of G. So the conformal class of G is the set of all metrics F times G, where F is positive, say. So all metrics conformal to G. Okay, so if you specify a metric up to conformal class, you're left with this function to solve for. And then the question is, how about the tensor k? What part of that is free? So there's a classic sort of decomposition of symmetric 0-2 tensors or 2-0 tensors, psi, decomposing it into three pieces. Psi trace is the trace part. Okay, so that's just the part of the tensor that holds the trace. And so then the sum of these two terms, which we'll define, is trace-free, symmetric and trace-free. Okay? So this piece here is called the transverse traceless parse. We said this yesterday. Traceless means trace-free. Transverse means divergence-free. So you want a tensor that's divergence-free and trace-free. And then there's this piece here, which makes up the difference. And that piece, the psi L part, is built out of the conformal killing operator. Okay, so this operator is defined here with indices down. The first part corresponds to the Lie derivative, and then this part makes it trace-free. Okay? So, I'm missing a W. See, that'll be fixed on the next set of slides. Okay, so, the next posting. There should be a W. No, that's right. No, there's W here. Sorry. It was always correct. Okay. All right, so if you have a W where this is 0, then that's a conformal killing vector. All right. So the idea is the trace part is determined, and psi is given. Psi L, there's a form for it, which means the difference of all those is the transverse traceless part. Well, it's traceless by the way this thing has been defined. So to make it transverse, you have to make sure the divergence is 0. Okay? So this part here, as written, may not have divergence 0. So you take the divergence and set it equal to 0, and that gives you this PDE system to solve. Okay? So you can correct the difference psi minus psi trace to be divergence free by subtracting off this longitudinal piece, this LW. So you want to show that you can solve this equation. Okay, so that's the proposition. Given such a psi, you can solve the equation for W unique up to the addition of a conformal killing vector. All right? But obviously, if you change this by a conformal killing vector, you haven't really changed that LGW, right? So if you add something in the kernel to psi L, you haven't changed it at all. Okay, so this is the proposition. Okay. So we'll sketch the proof a little bit just again to prove something. So this P sub G, did I write what it was? Okay. I guess I'll add this to the slide. So I don't know where it went. So, P sub G is the operator that you see here, right here. It's the divergence composed with the conformal killing operator. That's what that is. So it's a second order equation. Yeah?
Can you write it in indices because some students might be more comfortable with that? I can help you.
Oh, good Lord. Okay, right. So LGW is at least down, indices down. Is can we just leave this for homework? No, okay. So it's covariant derivative AB. So this is the Lie derivative part minus the divergence. So okay, so that's the conformal killing part, and then I think that's the slide I took out. This slide. Okay. So we're going to take the divergence. So let's say we'll put index A down. So the divergence means that there'll be one more index left. So we have I better use a different letter. I'll change this letter. How many letters are left? D. So I took a derivative. That's the C derivative. I changed that to a D. And then we have to trace on B and C. Okay, so there's, when you take a divergence, there's no covariant derivative on the G. That's 0. Good. Okay. Good. All right, so that's, and if you actually go through and check, I spared you the slide. So this operator is an elliptic operator from forms to forms or vector fields to vector fields, okay? And it's self-adjoint in terms of like an L2 self-adjoint. So let's go through the proof of that. That's important. So if you take this PGW and dot it with a vector field Z and integrate, okay? So all right, what is that? So that's LW, covariant, raise the index. That's what we did here. Okay. So you dot it with Z and integrate. Let's say M is closed manifold. So we integrate by parts and bring the C over to the other side with a minus sign. And do this out. Now, LW is symmetric. So you can symmetrize the derivative on Z. You just symmetrize it with a half. Not only that, LW is trace-free. So if you take this Lie derivative term and add a pure trace term to it, that's pointwise orthogonal to something that's trace-free. So we'll subtract off the trace part from it. So from this Lie derivative term, the Z term, we'll subtract off its 2 over n divergence times the metric and find that we get LZ right here. And of course, from this last equation, then, you see this is symmetric in Z and W. Okay. That's just a little trick. All right. So, oops, no, so, all right. So if you put W in here, all right, W, you get the first line. And I'll go back a slide. And then we'll go. So this argument used the fact that LW is symmetric and trace-free. So you could put any, in for LW, any symmetric tensor S that's trace-free. So we have LW, we have the divergence of it. So really what we proved is that Z, a vector inner product with the divergence of any trace-free symmetric tensor can be unwound like that. Okay? All right. Let's run through these bullets and we'll see if you have any questions. So by the Fredholm alternative or Hodge decomposition, so we have elliptic operator. The range of the operator, we're trying to prove we can solve a PDE. So we want to show that a certain right-hand side of the PDE is in the range. Okay? So the range is the orthogonal complement of the kernel of the adjoint, but it's self-adjoint. Okay? So the range is orthogonal to the kernel. The first identity here says the kernel of PW is exactly the conformal killing vectors to be in the kernel. All right? So now you know what the kernel is. The second identity says the divergence of a trace-free symmetric tensor is orthogonal to any conformal killing vector. If LZ is 0, then you have your orthogonality relation. So that means divergence of G must be in the range of P. And the equation we wanted to solve, the right-hand side, was divergence of a trace-free symmetric tensor. So that's the proof. Okay? Questions on that? So we have an elliptic operator like Laplacian, but this is a system. Anyway.
Could you please repeat why you use an elliptic operator?
I didn't say why. I mean, you have to compute the symbol of it. So you would, again, I'll put the slide up online, the slide with the proof that it's elliptic. But basically, you go to the operator, which is written on the board here, and you have to check that it's elliptic. So everywhere where take the derivatives away, everywhere where you see a derivative, you have to put in a symbol like from a Fourier transform, like xi b, xi c, right? Put that here, xi a, xi c, and then put it here, and then check that whenever xi is not 0, then that operator is an isomorphism on the fiber, and you check, and it is. It's not immediately obvious. It's just from. Okay. All right. So again, that theorem we just proved, you can also formulate it in asymptotically Euclidean spaces, with appropriate function spaces. But let's just do closed manifolds. We'll work in dimension 3 to keep the indices under control for a little while. All right. So that again, reminding where we are, we're formulating the conformal method, and we're going to give you the what is the free data for the conformal method in trying to solve the constraints based on the decomposition we just made. Okay? So first, I'll recall an identity from last time. You saw this a few times in the lectures and in several different places in several different dimensions. But in 3 dimensions, if you have a function, a metric g conformal to g0, then the scalar curvature is written this way. That's the conformal change of scalar curvature. And one of the exercises on the homework set will give you a hint on how to prove that if you haven't done so. Or maybe it just tells you to do it. But anyway, okay. One more conformal identity is useful in deriving the equations of the conformal method, and that is the following. And this one's just a computation. If you take 2 metrics that are conformal, and I'll take a 2-0 tensor xi, so indices up. You can also do a version with indices down. You can figure out what the power should be. But if you then take that tensor and then conformally rescale it by phi to the minus 10, okay? Take its divergence, right? So take a covariant derivative and then trace. With the metric g. That's the same as having done the divergence in the original metric g naught, and the phi to the minus 10 pulls out. Okay. So in particular, and that's for symmetric trace-free tensors. So if xi then is transverse traceless, okay, its divergence is 0, then phi to the minus 10 xi is also transverse traceless. Make sense? So, keep that in mind. All right, here's the data for the conformal method. So, the free data, again, is the conformal class of metrics. Okay? A scalar function tau, which is the trace was really the trace of the second fundamental form in the end, and then a transverse traceless tensor sigma. That's your free data. So any symmetric tensor can be written as the sum of 3 parts. Transverse traceless, the trace part, and this LW part. Okay? So the point is, the free data will be thought of as the TT part and the trace part, and then we'll solve for the W. All right? Based on that free data, you concoct the actual data for the Einstein constraint equations, the G and the K, by this prescription. G is conformal to your metric in your class, and then the second fundamental form K written up is this thing. Here's the trace part that gives you trace tau. This part here, notice the phi to the minus 4 G0 CD. That part, that's just G upper CD. That's just the rays of G. So that's the trace part, and then you've got the TT tensor, and then you've got the longitudinal part. All right? So the point is then you're going to solve for phi and W, and that'll be, the constraints will be 4 equations in 3 dimensions. So 4 equations, 4 unknowns. So we have to take these quantities and then stick them into the constraint equations. Okay? Let's do that. Well, let's do one of them, and then we'll hand wave the other one. You can. So we can immediately compute the momentum constraint operator. So I should have written up the constraints again, but let me just sort of say that one of the constraint equations, the vector equation, is this divergence of k minus the derivative of the trace of k. That vector or form has to be 0 in vacuum. That was one of the equations we derived. So we have to compute that quantity for this k. All right? Now, this tensor in here is trace-free and divergence-free. So we can use our previous conformal property to say, all right, to take the divergence of k with respect to the conformal metric, we can pull the phi to the minus 10th out and take the divergence with respect to the original metric. That's the divergence of the first part. The divergence of the second part, well, the divergence of g is just going to be 0. So you have the divergence, and then you have the tau. That's going to give you a derivative of tau. So that's where this part comes from. Then d of the trace, well, the trace of k is just tau. That gives you another d tau. Okay. Now, sigma is transverse traceless. It has no divergence, or 0 divergence. So divergence of sigma is 0. So all you get down here is divergence of L. Okay. That's your operator P. Okay. And then you combine these together. And so if you set this equal to 0, you then have the momentum constraint equation in the conformal picture. You also have to use you have to compute the Hamiltonian constraint. That involves the scalar curvature as well. And if you do that, you end up with this system of equations. So that's the conformal reformulation of the constraint equation. But now it's a determined elliptic system. So you can see the Laplace is here, and the divergence of L is here. I said it was divergence of L is an elliptic operator, but it is. All right. So you want to study this system, and if you can solve it, you've solved the constraints. The most successful case, in some sense, in terms of, I guess any case is successful. In the sense of having a complete picture of the space of solutions, is the case when you have constant mean curvature. And it's probably going to be an immediate letdown when we see how much of the equations go away. But point is, d tau is then 0 if there's constant trace. So constant mean curvature means tau is constant. So that's 0. And if you look at this, we know then that divergence of L of W is 0. We saw that the kernel of P is exactly conformal killing vectors. So if divergence of L is 0, then L of W is 0. Now, that equation might have no solutions, only the 0 solution. And it may have non-trivial solutions. But regardless, well, it doesn't matter. You might as well take W to be 0 because LW is what appears in the actual data. So if you're looking at the CMC case, you don't really even need the W part. And then LW is 0, so all you have is the first equation with no W in it. And that's the Lichnerowicz equation. Okay? So in the CMC formulation of the constraints, tau is constant, and all you're doing is you're solving this semilinear, nonlinear equation. So just make a couple comments, and then I'll sort of state a result about it. And this is in 3 dimensions. You can do it in higher dimensions, too. This equation enjoys some conformal invariance. So we said that the free data, part of the free data is the conformal class of the metric, the conformal class. And you can choose any representative in that class, right, morally speaking. So you might say, well, what if I picked a a positive function theta and picked a different representative in the same conformal class? Well, then it turns out, this might make sense, right? So if I then take my tensor, my TT tensor sigma, and give you the conformally related TT tensor for the conformal metric, and use that as your data, and try to solve the Lichnerowicz equation, what happens is you can solve the Lichnerowicz equation with phi for the original triple, if and only if you can solve it for this triple. And then the solution will differ by a theta inverse factor. Okay? So the bottom line is sometimes you might think there might be a best conformal representative to formulate the Lichnerowicz equation. So sometimes that is useful. And I'll talk about that in a minute. Also, again, as we saw in the CMC case, you don't really need the LW part. You don't have that. So if you just write the second fundamental form as the trace-free part plus the trace part, tau here is constant. And so the vacuum constraint is just divergence of the trace-free part is 0. So you're just looking for TT tensors. Okay? So here is a theorem, Shoke Braha, Amorohu, York, and then finished by Jim Eisenberg. And so this gives us the CMC, the CMC conformal method on closed manifolds. So let's look at a closed manifold, take CMC conformal data with tau, a constant, so CMC. Sigma is a transverse traceless tensor. G0, it marks a conformal class. Then the Lichnerowicz equation admits a positive solution. The Lichnerowicz equation is the constraint equation we have to solve for phi. If and only if, and the yeses and nos are as marked in this table. We'll talk about that in a minute. The solution is actually unique except in one case, where it's sort of, it emits sort of constant solutions. Let me explain what the y's are. So, well, of course, let me explain the easy part. So across the top discusses sigma and tau. So tau is a constant, so it's either 0 or it's not. Sigma is a tensor, so it's either always 0 or not never 0, or somewhere where it's not 0, okay, on the manifold. And depending on which case you're in and which Yamabe class you're in, you can solve or not the Lichnerowicz equation. So the space of metrics can be cleaved into classes, sort of equivalence classes. You look at your metric and you ask if some metric conformal to you has positive scalar curvature, 0 scalar curvature, or negative scalar curvature. And it turns out that's an equivalence relation. So I said earlier, or the last slide, that you can sometimes pick a nice conformal representative, let's say. You might pick one that has, for which the scalar curvature has a sign. Okay, so the theorem is that you can always do that. You can actually prove more. The resolution of the Yamabe problem by Yamabe, Oban, Trudinger, and Rick Shane, actually, in a given conformal class, you can find a metric of constant scalar curvature. Sometimes that's useful. It's often useful. Sometimes just having the sign is enough in the analysis. Okay, so I'm not going to go through the proof of this. I'll post it online. Some of it might already be posted. The no cases are very easy to establish. A couple of the yes cases are easy. The yes cases in the right part of the table, a couple of them are a little more subtle. I'll just say something about the method in Eisenberg's paper. So you're solving a nonlinear, semi-linear elliptic equation. The way that Eisenberg goes about it is a unified method using super and sub solutions. Okay, so there's a sort of a barrier method. You don't solve the equation on the nose. You produce functions phi plus and phi minus that don't satisfy the equality, but satisfy it with an inequality the right way, such that phi minus is less than phi plus, and phi minus is strictly bigger than 0. And if you can do that, it's a standard method, then by using an iteration argument, you can show there's a solution trapped in between. And having this lower bound be positive, that's important, will tell you your conformal factor in the end is positive. Okay, so that's the. There are various cases proved before, and then Heisenberg got them all by super and sub solution. Okay, so I'm not going to say anything about that. One slide here, just to make a comment. The non-CMC case is kind of interesting and a lot of interesting results, but it's not so clean and clear what the overall picture is. There are results when d tau is somewhat small in some way. So d tau being 0 is tau is constant, and we saw how to do that on the previous slide. When d tau is reasonably small, you can solve actually by sort of an iteration scheme where you can use this second equation. Given some initial phi, you can use the second equation to solve for a w, stick that w into the first equation and solve for a phi, and then go back to the second equation and iterate. Okay? And for the scheme to converge, you have to assume that d tau is somewhat small in a certain way. If that's not true, I mean, there are some results, some existence results by some of these folks listed here. And there are some results that indicate that the behavior of the conformal method is a little interesting in the non-CMC case, maybe unexpected, and there are a number of works on that. So it's a long story. Okay. So the last bit today and then tomorrow, we'll be talking about constructing constraints, solution of the constraint, say, by gluing. So the idea would be, if someone gives you a solution of the constraints, even let's say on a closed manifold, and then a solution on another closed manifold, or on asymptotically flat or whatever you want. The question is, could you produce a solution on the connect sum, for example? That's one question. Or as I mentioned yesterday, if someone gives you 27 solutions that represent isolated systems that are asymptotically flat, could you take them and kind of surger them together into a single connected solution of the constraints? Those are the kind of gluing kind of constructions we'll talk about. Again, the equations are nonlinear, so it's not just a simple superposition principle. So we'll talk today a bit about using conformal methods to do gluing, and then we'll move on from there. I'll just sort of say, when you use conformal method, you solve elliptic equations like equation involving the Laplacian we saw earlier. And in such situations, the deformations are global. Your conformal factor, or whatever your deformation you solve for, you basically start with two solutions, you make some approximate solution, and then you find a conformal factor, let's say, to fix it to an exact solution. When you do that, your conformal factor is generally, whatever it has to be to solve the equation. It doesn't necessarily have to be conformal factor equals 1 on this piece. It probably isn't. Which means that the original data over here got moved somehow, maybe a little bit. So then you can ask the next question would be, well, could you take data, solutions of the constraints, can you glue the manifolds together, produce a solution of the constraints, and then preserve the data exactly outside the gluing region? So obviously you need something that's not conformal to do that. So we'll mention some results and some of the ideas of the technique. Okay, so I'll say just a slide or two about the IMP gluing and then mention a related result and try to throw out some of the ideas of the proof so you can see it. It gets a little bit technical, but there's a few geometric ideas, PDE ideas I can mention, maybe give you an idea of the flavor of things. All right, so Eisenberg, Mazzeo, and Pollack developed the gluing, not just for closed manifolds, but for more general situations. for gluing solutions that are constant mean curvature using the conformal method. So solutions of the constraint equations where the trace of k is constant. So they wanted to take solutions like this and glue them together. All right. So you could do this in higher dimensions. We'll stick to 3 for the moment. Given a 3-manifold sigma, and that sigma could be the union of 2 disjoint connected pieces, or sigma might be, 1 given, manifold to start, and you mark 2 points, so 1 on each component, or if you're on sigma, you pick P1 and P2 points on your manifold. And then you either want to do a connect sum of 2 components, or you want to add a handle, okay? And say that the corresponding manifold you get with the surgery or whatever, that admits a solution of the constraints. And the idea is that at least away from the gluing region, the solution should resemble the original. Maybe not be equal to on the nose, but be close. Okay? All right, so if you have a solution of the constraints, gamma and k, and that represents gamma and k is the part on the disjoint union 2 or on the one piece, is a solution of the vacuum constraints. Tau is a constant, which means the second fundamental form can be decomposed into trace-free part and trace part. All right. So what's the sort of general idea of the proof? All right. So So you start with, I'll just draw one piece. You start with a manifold and a point and a little neighborhood. And what you do is you take a neighborhood of a point and you kind of look near the point, look in normal coordinates near the point where you understand what the metric looks like. And then you do a conformal rescaling to blow up the little neighborhood around the point into a long sort of end. And you rescale it so that the end really is asymptotically cylindrical. Okay? Now, if it's, and I'll write up a couple equations for the next theorem. So if it's asymptotically cylindrical, then if you go out far along that end, if it becomes more and more cylindrical, then at some point, you can then actually modify it to make it an exact cylinder. Do the same thing on the other piece, and then just stick them together. That sounds easy. But that hasn't solved the equation yet. So again, you conformally blow up to produce an asymptotically cylindrical end. You rescale the TT tensor conformally, so it's still a TT tensor then. You still solve the constraints. So by doing a conformal blow up, you can preserve the constraints. But to glue together, then, you do something non-conformal. You, far enough down the end, you transit the metric you got from the conformal blow-up to an exact cylinder. That's not conformal. That's not, okay? So now you're not quite a solution. But you sort of have a large parameter t that tracks how far down the neck, how long the neck is, how far down until you transit to a cylinder. And then you produce an approximate solution. Okay, you produce an approximate solution of the problem by patching the 2 metrics and tensors together. And also the conformal factor, you're going to use a conformal factor, you sort of patch them together too. You got to do something to then perturb the approximate solution to an actual solution. All right, so I just want to mention sort of one part of this, then I want to move on to a later one where I can show you some of the details, is at the end of all this, what you have is a manifold, a metric you patch together, a positive function related to the conformal rescaling you did, right? So to get this sort of scenario, you had to use a conformal factor that blew up the neighborhood, and then, outside a neighborhood, that conformal factor could be 1 over here, and then has to blow up near the point. When you actually glue them together, then you have a patching. All right? So you've got manifolds, you've got metrics, you've got tensors, you've patched them together, you have an approximate solution. What do you have to do to correct it? Well, the first thing is, now that you've gone outside conformal deformations, so outside the conformal class now, the tensor you've now patched together isn't TT anymore. Right? So if you have a TT tensor and you do a conformal transformation and blow it up or multiply it by the right conformal factor, it stays TT. We mentioned that earlier. Okay, but now when you're doing these deformations outside the conformal class, you lose that. So it's not transverse traceless anymore. You have to fix that. How do you fix that? Trace-free, symmetric, but it's not TT anymore. So what do you do? Keep flipping slide. And what do you do is, you use that LW, divergence of LW equation, to fix it. All right? So you correct the fact that it's not TT by perturbing the tensor by an LW. Okay, solving that like we did before. That's why I introduced that earlier. And then you solve the Lichnerowicz equation for a conformal factor. Okay? And once you've done that, you've got a TT tensor, which is the original tensors soldered together and then corrected by the method to using a vector field. And then you use this conformal factor to reconstitute the data as in the conformal method. Okay? That's just the idea. Outside the neck region, the metric you get, gamma t, approaches the original metric, and the second fundamental form approaches the original k exponentially fast in t. So in that sense, the theorem is that, all right, you can put these together, and outside the gluing region, the data will look close to what it was originally. Okay, that's the setup.
And Justin, so t is really corresponds roughly to the length of the neck. So you need to make the neck very long.
You have to make the neck very, and that sort of that separates the two pieces and allows you to shield one from the other, kind of, right? So as I'll point out on an upcoming slide, so the neck gets long, but that's not. So this picture, and this is very important. This picture isn't the final geometric picture, right? So this is the picture in the conformal picture, right? So actually, you have these two manifolds connected by a long cylinder that's only in the conformal class. So the conformal factor actually makes the geometric connection between these two manifolds actually looks more like a deformation of a short shield, very small. So actually,
it's not very long.
Geometrically, it's not very long. Yeah.
But it's very small.
It's small. Yeah. In the end. Yeah. So I'll show that on an upcoming slide. All right. So this looks scarier, but it's actually simpler. So I just want to look at so we can avoid the K. I'll just look at the G, the metric scalar curvature gluing. So CS, a conformal gluing here, we'll just look at constant scalar curvature gluing. Okay? Constant scalar curvature metrics correspond to solutions of the constraint equations with K is 0, but say, for example, lambda, the cosmological constant, could be non-zero. Okay? So suppose you want to do this gluing procedure, but you don't care about K. K is 0. You only care about G and having constant scalar curvature. Okay? So consider your two manifolds. Here we have two manifolds with non-empty boundaries. This is I'm stating this in the way that in joint work with Mikhail and Pengzi Miao. There's also localized gluing or conformal gluing and involving conformal and non-conformal methods by Piotr, Jim Eisenberg, and Dan Pollack. So consider two compact manifolds with boundary. Okay. Take your marked points. Assume each metric has constant scalar curvature sigma n which is normalized to be negative, this negative number, 0 or positive. Okay? In the case sigma is positive, we assume the first Dirichlet eigenvalue of this operator, so basically Laplace plus n, is positive. Okay? For the other eigenvalue signs, that's automatic anyway. All right? Then, and I'll point out that that's always true if that Laplace plus n has positive spectrum if you're doing this on a very small disk around a point. You think about that. But the result is there's a family of metrics parameterized by t on the connect sum with constant scalar curvature. So you've solved the vacuum constraint maybe with lambda, with the metric approaching the metric on either piece outside some given region, and in the version that in the joint work, you can say the volume of the overall configuration is close to the sum of the two volumes. So adding constant scalar curvature even with the volume constraint. And that's, so, you know, again, you're asking about the tube and the geometry. If you can make some comments about what parts of the geometry you can kind of preserve. So you can preserve volume. All right, so,
Question?
yeah.
This is conformal, right? So
This is conformal, yeah.
Isn't exactly.
Right, and then so then in next lecture I'll mention that you can then put this together with non-conformal, which is originally done by Crucial and Delay to sort of take this conformal method and non-conformal methods to localize. So still, in this theorem, outside the gluing region, the metric is close to what it was, converges to what it was originally, but it's not equal to it on the nose. Okay. So I want to put up a few slides to show you what some of the details look like. Okay, so.
Why do you need non-empty boundary?
So again, it works if you're closed, then you have one of these conditions too. So the boundary, when you go through the proof, you have to show some operator has to be invertible, and then if it's never invertible, and maybe we'll get to this slide, maybe we won't, but if it's never invertible, then in a limit, you produce a solution of Laplace plus n equals 0 with 0 boundary conditions, and so that allows you to rule that out. So you don't really need non-empty. It's convenient. It's useful for other gluing constructions because, in one sense, it's not that limiting because, as I'll point out maybe next time, if you're doing a gluing where in the end you want to localize, you might say, all right, I'm going to glue these things together, and I'm going to glue them together. I'm going to start with 2 small balls picked on each manifold, and then glue there. And then if you pick small enough balls, for example, then that hypothesis there is automatically satisfied. You can glue them, and you'll see next time that maybe if you can localize some deformations, you might be able to patch it into the rest of the manifold. So if you have this big manifold here and this little ball, and you've solved the gluing on the ball, maybe you can patch it to the rest of the manifold that was there and then figure out how to fix it where you glued along an annulus or something. So that's what we're getting there, but I mean, that's a good question. All right, so how do you conformally produce this picture of the manifold? So first of all, G0, again, when you see this, that's the metric on the unit sphere. Okay? So it's like D big omega squared, maybe. So what you do is you go to normal coordinates. In normal coordinates, the metric looks close to flat. So it's basically dr squared plus r squared times the metric on the sphere. So what you do then is you blow up your metric by multiplying by r to the minus 2g, where r is the distance to the point. And when you do that, you produce something which is asymptotically cylindrical. You might say, is it? I don't know. So this piece q has first derivative in value 0 at the center point, so this part's okay. What about this part? So obviously, you have dr over r squared, so you want it to be ds squared. So s is log r, basically, well, minus log r. And that'll make this piece look exactly like a cylindrical metric. It's convenient to make s be equal to this thing. r is a fixed number representing the size of a ball in which we're doing this gluing. So this is just a constant. That's r, distance to a point, and this t is a parameter that'll basically measure the length of the neck in the conformal picture. All right, so after you've done this rescaling, your metric looks like ds squared plus sphere plus some perturbation term, okay? We're going to write the r to the minus 2 as, or the r squared as, well, that's the form of a conformal factor in n dimensions. So we'll write it that way, side of the 4 over n minus 2. Okay? This piece here, the cylindrical part, I'll call GC tilde for cylindrical. All right. So again, what you do is, so you have this region, this long interval from t is large. So minus t over 2 to minus 1. Then you're going to go all the way to 0. And then on the other half, it'll go from 0 out to capital T or something, or t over 2. So you transition smoothly from this approximately cylindrical metric to the actual cylindrical metric inside this region. So you've got minus t over 2 to minus 1, minus a half. Now you're exactly cylindrical here. And then you'll do that on the other end too, and then put them together. Okay? Let's see. Right. So once you do the same for the other end, here s is negative. Here's your s-axis. It's negative. On the other end, if it was negative 2, that's one thing. But then you want to put them together, so you have to have an s to minus s identification. When you do that, I'll point out that the error term here involves an e to the minus 2s. And then if you've got two of them added together, but s goes to minus s to make the identification, you end up with a cosh on that term. So that's your error term from cylindrical. And in the middle core piece, from minus 1 really to 1, on the other end, you're exactly cylindrical. Okay. So, great. So you have your metric, gamma t. You want a conformal factor. You now just want to find a conformal factor to multiply to make your scalar curvature constant. That's the goal. All right? So we're going to first build an approximate conformal factor and then deform it. Okay? So often in nonlinear equations, you try to build something which approximately solves the problem and then figure out how to, often using linear analysis, how to perturb it to an exact solution. So the approximate conformal factor might not be what you think exactly. Let psi t be the following. So you're going to take psi 1 and psi 2. Those were the conformal factors, let's call psi 1, let's say, that blew up each piece individually. So psi 1 equals 1 away from the gluing region. Inside the ball, psi 1 was equal to roughly r to some power. Okay? So you take those conformal factors, and what you do is, to produce the approximate solution, in the neck, you actually have the approximate solution, psi t, look like psi 1 plus psi 2 in the neck region. And then outside the neck region, psi t is roughly 1. Okay, so that won't change the data too much outside the neck. What that means is, and this part's kind of cool, so inside the actual cylindrical region, we have psi to this power for the conformal rescaling, which is r squared. Inside near the marked points, okay, r equals this. So here's your equation for s. You got some logs raised to the power. R satisfies this equation. Now, on the other end, you have to make s minus s. That gives you a plus s. Okay? So when you add them together then, you need a license for this thing. Okay, so when you add them together then, psi 1 and psi 2, plug in, you get this for psi t. That's the equation for psi t sort of in the middle. So now you compute. I said this is an approximate solution. What does that mean? That means you take your metric gamma t, right, which again transitions from whatever, from the conformal method, from the conformal metric that you blew up to the cylindrical metric way down the neck. You have what I call an approximate solution. What the heck are we solving now? That was a couple slides ago. So you want to take scalar curvature of the thing and show that it's equal to sigma n, that constant. That's what you want to solve. So this is the friendly formula for the conformal change of scalar curvature. All right. In a large piece down the neck, we know an exact formula for psi. Exact formula. In the middle, even further down in the middle, we know the exact form for the metric gamma t. It's cylindrical. The Laplace operator for gamma t, well, what is it? It's a sum of two metrics. So you're going to have second derivative in S plus the Laplace operator on the sphere. This metric only depends on the S part. So you have two derivatives in S. So all you get is n minus 2 over 2 squared times this factor back again. So in the middle piece, you can compute the Laplacian of your conformal factor. And this is a cylinder. So the scalar curvature is n minus 1, n minus 2. All it is the scalar curvature of the sphere piece. Right? The line part doesn't give you any more curvature, just on the n minus 1 sphere. So if you take this and this, stick it into here, you get 0. Okay? Now, here's what I mentioned to Piotr earlier. You want to say, what does the geometry in the approximate solution look like in between the manifold? Does it look like a cylinder? No, you have a conformal factor. It actually is, on the nose, a Schwarzschild neck of mass, this mass. So it's exponentially small in t. So you've got a very small Schwarzschild neck. We drew a picture yesterday going up the board this way. I'll draw it this way. So you've got a very small Schwarzschild metric. This is the piece in between that's gluing the two manifolds together. Now you might say, wait a second, I don't want to solve scalar curvature 0. How is that actually a solution, or an approximate solution? And that really goes, and I'll sort of finish up on the next slide. But the cool thing is that the neck is exactly Schwarzschild. Okay, we want to solve this nonlinear problem. We want to solve this side here is sigma n. Okay? So I'll put sigma n on the left side of the equation for the constant and move this nonlinear term over here. And that's my nonlinear operator n sub t. I put sigma n here, and I had this power of the conformal factor with that term. Let me flip back one. So put sigma n here, take the conformal factor to this power, move it over. Okay? That's this nonlinear operator. You want that to be 0. You want to solve for a small eta to change your conformal factor to get this to be 0. And the point is, you can compute this in the neck region, we know what it is, and in other places, and this thing is exponentially small. All right? And so, without a proof, a contraction mapping argument will give the solution, but to build your contraction mapping argument in the right spaces, you need to analyze the linearization of this nonlinear operator. So the first two pieces are linear already. This piece, when you linearize, you take a derivative, it brings down a factor of n plus 2 over n minus 2, so you have something here. Right? And then you get an f here, and this power of psi t. You linearize the operator at your approximate solution. So at this point, you have to analyze this operator. And I'll finish by saying, there was a question earlier about the Dirichlet problem or something. So what you have to do is say you want these operators to be invertible and sort of uniformly invertible, so you have to analyze what happens for large t. Analyze how these operators converge, these operators, how this operator converges, both in the neck region and sort of in the punctured manifolds when you take the limit. And you can do that. And that analysis leads you to be able to prove that you can solve this nonlinear equation for large t. All right? I'll stop there. We'll finish up tomorrow. Thanks.